Okay, so continuing with chapter 7, now we're going to look at some information to help us understand the acidity of protons at the terminal carbon for a terminal alkene, a terminal alkyne, and an alkane, and comparing the acidities, and then specifically discussing the acidity of the alkyne, terminal alkyne proton, and how we can use this acidity to do further reactions with alkynes. So we need to recall the definition of electronegativity. Electronegativity is the ability to withdraw electron density towards one's self. The ability to withdraw electron density. So when we are comparing the relative electronegativities of carbon atoms, it is important to be aware that the most electronegative carbon is an sp hybridized carbon, followed by sp2 and sp3. And this is why the pKa of an sp carbon to hydrogen bond, so the sp carbon to hydrogen bond has a pKa of 25, where the sp2 carbon to hydrogen bond has a pKa of, I think, 40. I might have to go back and look. It's the pKa of the carbon to hydrogen bond for a sp2 carbon is about 44. And the pKa for an alkane carbon, an sp3 carbon to hydrogen bond, is greater than 60. And that the reason for those pKa's is the electronegativity. So for an sp carbon is more electronegative, meaning that it is withdrawing electron density from the bond that holds hydrogen, and that causes that to be a weaker bond. So if the bond between carbon and hydrogen contains less electron density, because the sp carbon takes it, then it has a weaker carbon to hydrogen bond, and the pKa is lower. So we consider an alkyne proton to be weakly acidic. And we can exploit this acidity in reactions. So here we go. These are the pKa's. The pKa of the proton in ethine is 25. Okay. So 25 for this proton. Then we have for ethene, for a double bond, the pKa of the terminal proton is 44. And for ethane, the pKa of the terminal proton is 60. So how can we rank that amongst our acid strengths in the chart that we've already looked at? An alkyne proton is more acidic than an amine but less acidic than water. And then let's draw what the conjugate bases would be. So for HF, the conjugate base would be fluorine or fluoride ion. F minus. For water, the conjugate base would be hydroxide ion. For the alkyne, the conjugate base would be an acetylide ion. For ammonia, the conjugate base would be amide ion. For the alkyne, for the alkene, the conjugate base would be an alkenyl ion, anion. And for the alkane, the conjugate base would be a carbanion. Now, in terms of the strength of the conjugate base, so these are the conjugate bases. It will be the reverse of the acid. So the strongest base corresponds to the weakest acid. So all of our greater than signs are going to be opposite than they were with the acids. And fluoride is going to be the weakest base. Since it is the strongest acid. And the carbanion, the ethyl carbanion, is going to be the strongest base. So you're going to have to still be able to rank acids and bases from weakest to strongest, given a list. And now your double bond and triple bond carbons should be included in your ability to rank from strongest to weakest. So, acetylide or terminal alkynes are weak acids. They're stronger acids than water, but weaker acids than ammonia with the pKa 25. So if we want to exploit the reactivity of the acidity of the terminal alkyne, we need a base that is sufficiently capable of removing the proton. And that means that the conjugate acid of the base that we choose has to be has to have a higher pKa than the acid we are trying to, the acid proton that we're trying to remove. So what I'm saying is that we can choose amide ion as a sufficient base because ammonia has a pKa of 35. So the base that we use, its conjugate acid, should have a higher pKa than the acid proton that we are attempting to remove. So amide ion is a sufficiently strong base to remove the alkyne proton because ammonia has a higher pKa than the alkyne. When we react the alkyne with the amide ion, your book will almost always represent the amide ion as sodium amide. And so this is where I'm telling you to be careful. And I told you not to get sodium amide confused with sodium metal and liquid ammonia. They do different things. Okay? If it's an NH2, the reaction is we're removing the acid proton. If it's an NH3, then we're trying to make a transalkene from the alkyne. Okay. So with the amide ion, we remove the acidic proton shown in purple, and we create the acetylide ion and ammonia. Remember that in order for the reaction to proceed, it should go from a stronger acid to a weaker acid. So we have pKa of 25 here and a pKa of 35 here. The reaction producing the acetylide ion then is favored. So we can't use hydroxide ion. It's not basic enough because H2O, using hydroxide ion to remove the proton would produce H2O, which is a stronger acid than the alkyne, and so equilibrium would favor making the protonated alkyne. Okay. Last thing, and then I'll pick up again on the same topic next time. What if you can make an acetylide ion? That acetylide ion will react with haloalkanes to make a longer carbon chain. And that's where we'll pick up on the next video.